Hi, my name is Kyra Henriques, and I'm a junior from Oviedo High School, and my research involves the development of an automated ferrofluid-based prototype for the extraction of microplastics from aquatic environments. In 2015, there were an estimated 51 trillion microplastics in aquatic environments. One area of great concern is the Great Pacific Garbage Patch, which is estimated to be around 2 times the size of Texas. This patch includes a lot of dense plastics. Plastics can degrade down through UV radiation as well as weathering into smaller plastics, including microplastics. Microplastics have been found everywhere. They've been found in fish, drinking water, bottled water, as well as in our bodies, including our lungs and in our blood. So when microplastics enter the environment, they can serve as sorbents for harmful chemicals. In addition, as more and more organisms consume microplastics throughout the food chain, this can lead to the bioaccumulation of microplastics. They can also lead to a multitude of health implications for both organisms and humans, including oxidative stress, inflammatory lesions, respiratory problems, cardiovascular disease, as well as an increased risk of cancer. So current methods to extract microplastics include sieves, membranes, and booms. However, all of these methods have low microplastic removal efficiencies, are costly, labor-intensive, as well as limited and widespread usage. And because of this, researchers are currently looking for alternatives to these methods. So in my research, I came across ferrofluids, which are combinations of magnetite and oil, which have been recently investigated for their ability to facilitate the magnetic extraction of microplastics from water. So when oil and magnetite come in contact with one another, there's an attraction between the two. Scientists are not exactly sure what this attraction might be because of, but two proposed mechanisms of action include physisorption and chemisorption. And through this attraction, the oil can act as a surfactant on the magnetite. So when this ferrofluid complex is formed, when it comes in contact with the microplastics, since both microplastics and oil are hydrophobic in nature, there's a like-to-like attraction between the two, and the microplastics act as a sorbent for the oil. So more onto physisorption and chemisorption. Basically in physisorption, what happens is the iron oxide enters the water and the surface oxygens are protonated. And these newly formed hydroxyls have an attraction with the carbonyl group of the fatty acid through electrostatic interactions. In chemisorption, the carbonyl group and the oxygens of the iron oxide form coordinate covalent bonds, and this creates the ferrofluid complex. So since a lot of microplastics are formed through environmental degradation, this can cause for them to become more porous. So when the oil from the ferrofluids come in contact with the microplastics, they can be either absorbed into those pores or adsorbed onto the surface. So given the advantages of ferrofluids, with its components being widely available as well as cheap, I wondered whether automation of this using ferrofluids would be possible. This leads me to my research goals. The first goal of my research was to design and develop an automated ferrofluid-based prototype to magnetically extract microplastics from real-world environments. And in order to do this, I needed to determine an optimal ferrofluid combination that would yield the highest magnetic removal efficiency and use this in my prototype. I used several different combinations of ferrofluids, cooking oil both used and unused, and engine oil both used and unused. I used 4 volumes of oil and 4 weights of ferrites, and I tested each of these combinations efficiency in removing 3 commonly found microplastics in aquatic environments: polyethylene, polypropylene, polyethylene terephthalate. I made all the microplastics that I used in my experiment from scratch. Polyethylene, I got them from Ziploc bags. Polypropylene, I got them from food packaging containers. And polyethylene terephthalate, I got it from fishing line. Now onto the synthesis and analysis of my ferrofluid combinations. So I started off with a microplastic suspension, which was 0.5 grams of microplastics per 1 liter of water. I added oil and ferrites to the solution, and I vigorously stirred the solution in order to maximize contact between the ferrofluids and the microplastics. I used a series of 20 neodymium magnets encapsulated by a test tube in order to extract the ferrofluids with attached microplastic, and I vacuum filtered these final solutions and weighed the amount of microplastics were remaining after magnetic extraction was complete and compared this with the initial weight. And here's an image of all the neodymium magnets that were used in my contraption that were able to extract the ferrofluids with attached microplastics. So I use a magnetic removal efficiency formula here, which is basically the percent change formula, where CI stands for the initial weight of the microplastics added to the solution, and CF stands for the weight of the microplastics in the solution after magnetic extraction is complete. I had 3 controls in this experiment: 2 positive controls, a 1 millimeter sieve, and the second one was no oil added and just increasing weights of ferrites. and a negative control where no oil was added and no ferrites were added. And I conducted factorial analysis in order to analyze the effects of each of the 4 factors: oil volume, oil type, ferrite concentration, and plastic type on the magnetic removal efficiency. And I found that out of all those 4 factors, ferrite concentration did not have a significant effect on the magnetic removal efficiency within the tested range. However, there was a positive correlation between the ferrite concentration and the MRE. And this is further corroborated in the main effects plot here. The possible explanation of these results is because when the ferrite concentration is higher, there's a stronger magnetic field. Therefore, more microplastics can be trapped and more microplastics can be extracted. From the other 3 factors, all of them had a significant effect on the magnetic removal efficiency, so I decided to graph them onto these graphs, as you can see here. And I found that cooking oil had the highest magnetic removal efficiency for all 3 microplastics. In addition, I also found that the unused oils had a higher magnetic removal efficiency compared to the used oils. Lastly, I found that there was a strong negative correlation between the oil volume and the magnetic removal efficiency. And this result is further corroborated in the main effects plot here. So cooking oil had the highest magnetic removal efficiency, and the reason why I think that this might be is because peanut oil has a high fatty acid content, and because there's more fatty acids, this can lead to a better surfactant ability. Since the used oils had a lower magnetic removal efficiency, I believe that this might be because when oils are used, they undergo a lot of heating processes, which may alter some of the bonds, decreasing the surfactant ability of the oil. In addition, as the oils are used, the viscosity will increase, decreasing the ability of the oil to enter the microplastic pores via capillary action. I also conducted an IOL staining of fluorescence, where I used a compound light microscope and an orange lens and a blue light LED in order to excite the microplastics, and I got these images as you can see here. I determined that the optimal ferrofluid combination to use in my prototype included cooking oil, 0.5 milliliters per liter of oil, as well as around 1 gram per liter of ferrites. And this is a schematic of my prototype, and the goal of my prototype was to completely automate the process that I had done or performed manually in the prior part of my experiment. It was powered by a Raspberry Pi, as well as had a series of stepper motors, as well as pumps and containers to move the oil and water from one container to another.
Now I will show you my prototype in action. The microplastic water in the oil has already been added to container 2. The ferrites are then added to the container and the stirrer turns on, which creates the ferrofluid as well as mixes the microplastics within the water. The electromagnet is then turned on and lowered into container 2. Using horizontal and vertical movements, the electromagnet is moved up and down. The electromagnet is then lifted up in intervals to pick up ferrofluids with attached microplastics. The electromagnet then skims the surface of the water. Now it is lifted up and horizontally moved to container 3. It is lowered into container 3. The electromagnet is then turned off, which releases the ferrofluid waste into the container. The electromagnet is then moved back to its original spot and the clean water is pumped to container 4.
So after running this prototype for a total of 5 trials for all 3 microplastics, I'm happy to report that there was a greater than 85% magnetic removal efficiency observed. In addition, I found that there was a range between 20 to 30% increase in the magnetic removal efficiency of my prototype compared to the commonly used 1 millimeter sieve, which is used to extract microplastics today. So overall, I was able to engineer an automated prototype that incorporated the best performing ferrofluid combination, and I was able to determine that automation of the use of ferrofluids is possible. In the future, I would like to do now-red staining visual quantification in order to test my prototype using real-world applications, as well as optimize my prototype to be used in the real world. So now on to scaling up the prototype. The current cost of the prototype is around $656. When scaled up, it's predicted to be around $1,392. However, although this seems like a lot of money, there are a lot of advantages to this prototype when scaled up, including the longevity of its parts, the less human interaction that is required, as well as the fact that it's completely automated and can be used continuously to extract microplastics. So some limitations of my prototype currently is the possible magnetite release into the environment. In order to eliminate this issue, I would use a Y-type strainer as well as or a second electromagnet to remove the ferrites before the water is released into the environment. Another possible concern is the release of oil into the environment, and to combat this issue, an oil skimmer which has a hydrophobic coating on the stainless steel belt can be used to extract or to make sure that all the oil is completely gone from the water. So here's an image of my final or my scaled up prototype. So what are the implications of my research? I found that automated aquatic microplastic extraction is possible and highly effective, as well as high microplastic removal efficiency can be achieved. And my prototype has many advantages, including less manual involvement, widespread use, as well as cheap ferrofluid costs. My prototype can be implemented in several different applications, including container ships, oil rigs, Coast Guard and government boats, as well as in water treatment plants. Thank you.